All right. So as we look at simple harmonic motion, we need to talk about energy. So potential energy of a spring, 1/2 kx squared. We talked about that. Total mechanic energy of a spring is going to be a combination of the kinetic energy of the spring plus the potential energy of the spring. Total mechanical energy will be conserved as we are assuming each system is frictionless. So if the mass is at the limits of its motion, the energy is all potential, either all the way compressed or all the way open. If the mass is at the equilibrium point, the energy is all kinetic. So we know that the potential energy is at the turning points, okay? And that is 1/2 k amplitude squared, because the amplitude would be the distance off of the equilibrium. Hopefully that makes sense. And you can see from the screens there. So pause and take a look at that. The total energy is 1/2 k a squared. So we can write everything here. Now this can be solved for the velocity as a function of position, all right? So the velocity at any time is equal to positive negative v max divided by the square root, or times the square root of 1 minus x squared over a squared. V max is equal to the square root of k over m times a. This equation is helpful when we talk about SHM in a spring system, okay? Max velocity, so that's the velocity going to be right in the middle, right? Right in the middle of the equilibrium. It's going to be this. If we look at the projection onto the x-axis of an object moving in a circle of radius a at a constant speed of v max, we find that the x component of its velocity varies as v equals this. This is identical to SHM. So when we look at something traveling in a circle, this is what we get. Therefore, okay, now I'll take a step further, we can use the period and frequency of a particle moving in a circle to find the period and frequency. So, period of SHM is this, 2 pi square root m over k. This is for a spring system. And then frequency is just going to be the inverse of the period, which is 1 over 2 pi square root of k over m. You can learn both equations. I would much rather learn this one and then just take this to be frequency, but your choice. And then we can find position as a function of time using some things that we've done previously. So x would be a cosine angular velocity times time, a cosine 2 pi frequency times time, or the way we can look at it, a cosine 2 pi t over the period, okay? But any of those would suffice when we talk about position as a function of time. Now, if we graph this, so if we had this up and down motion, okay, and we graphed it, the bottom of the curve is the same, but shifted 1/4 period, so that is the sine function rather than cosine. So you can see here, if we're moving this thing up and down, we have paper moving and we have a pen attached to it, right? We see that equation. And then we can also get a sine curve if we shift it. The velocity and acceleration can be calculated as functions of time. The results are below and are plotted as left. So here we got displacement, velocity, which is everything shifted over 1/4, and then acceleration, which is just going to be the inverse of the displacement. You can see here how it works. So the equations are here, but here's what I want you to see. So displacement curve, shifted 1/4 over, you can get the velocity curve, or flip it to find the inverse, which would be the acceleration curve. And then you can see the math here to try to find what the velocity is, negative v max sine of 2 pi t over period, or the acceleration, which is max acceleration cosine 2 pi t over period. So let's do some examples here. So we're going to double the amplitude. Suppose that this spring figure here is stretched twice as far. So x is 2a. what happens to A, the energy, B, the maximum velocity, and C, the maximum acceleration? Do it now.
All right, so in this example, we see that the amplitude is going to go, instead of stretching to A, we're going to stretch it to 2A. And so we want to talk about energy, velocity, and acceleration. So I'm just put a couple equations on the board that will help us do that. Energy is 1/2 k amplitude squared. If our amplitude's A, then energy is just going to be what it is. But if we double it to 2, all right, energy going to be 4 times as much, because 2A squared would be 4A squared, right? So it'd be 4 times as much. So energy would be 4 times as great when we double the amplitude with our stretch. Velocity. If we look at velocity, A is here. If A is 1A, velocity is what it is. If we double the amplitude, the velocity doubles. Again, with everything else staying constant. And then acceleration and force. So if we increase the amplitude, the force increases. In Newton's second law, if force increases, acceleration will increase, which should make sense because of our velocity increase and our acceleration also should increase. But that's the reasoning behind that.
More spring calculations. So we're stretching it 0.15 meters when a 0.3 kilogram mass is suspended from it, so it goes from equilibrium down. The spring is then set up horizontally with the mass resting on a frictionless table. The mass is pulled so that the spring is stretched to 0.1 meters from the equilibrium point and released from rest. We want to find K, the amplitude of the horizontal oscillation, C, the magnitude of the maximum velocity, D, the magnitude of the velocity when the mass is 0.050 from equilibrium, so what's the mass going to be on its way back, and E, the magnitude of the maximum acceleration of the mass. Lots to do, but we'll just tie it all into one problem. Do it now.
All right, so I'm gonna read through this as I do it, just so you can see where I'm at each step. A, B, C, D, and E, and I have formulas up there. So A says we want to find K. We want to solve for K, the constant for the spring. Hooke's law of force equals K times X. I want to solve for K. So K is equal to force over X. Force is just mass times G over X. So now we'll substitute everything in. The mass is 0.3 kilograms. G is always what it is, so I guess we're on Earth, right? And then our distance, we stretch it, is 0.150. And if we type those into our calculator, you can do it with me. Nice, easy, 19.6 newtons per meter, right? Yeah, see, that's the units I have. Okay, so we just use Hooke's law to find K. So now we go to B, and B says, what's the amplitude of the horizontal oscillation? All right, and so as we look at this, it says it's stretched to 0.1 meter from the equilibrium point. That means our amplitude is how far we stretch it. So there's no math involved. It's essentially just reading the problem. As you read the problem, you should see that the amplitude is going to be 0.1. C then says the magnitude of the max velocity. V max is A square root of K over M. So I'm going to substitute in, and then you can solve. Our amplitude is 0.100 square root of K, which is 19.6, divided by our mass, which is 0.3. So V max in this case is 0.808 meters per second. So that's the speed it's going to have when it's going its fastest, right? When it's right at the equilibrium point. And then D says, what's the velocity when the mass is 0.05 meters from equilibrium? Okay, so it's going to be a little less, all right? But we got to know V max to do that, which we know. Of 1 minus. Now this X This x number is just how far we are from the amplitude, which is 0.05 meters. All right, not what I said. Yep, and then a, we figured from above, is 0.100 squared. So that's how far we are from the equilibrium, and then this is the equilibrium point, or the amplitude. And so our velocity at that time will be slower. It's at 0.7 meters per second. And then letter E is asking the magnitude of the max acceleration of the mass. So we want to find max acceleration. It's force max over m. Now force is kx, right, from here. So now we substitute in our 19.6, our amplitude of 0.100, and we divide that by 0.3 kilograms, which is the mass. And again, calculate and solve, we should get 6.53 meters per second squared. So really quick, let's talk about this. So you got the spring here, right? And you stretch it to here. So when it reaches the equilibrium point, that's when this and this are occurring. This is occurring somewhere before the equilibrium point, okay? When we talk about the spring. So that's what when we talk about that fastest point, that's where we're going to be at the equilibrium point.
And then for simple harmonic oscillator that we've talked about, we want to find A, the total energy, and B, the kinetic and potential energies at half amplitude, where amplitude is divided by 2. And we'll talk about those numbers. Do it now.
All right, so our spring system from before, now we want to calculate the total energy and the kinetic and potential energies at A/2, or halfway amplitude. So essentially we got our oscillator, and so here's A, and then this would be approximately half to A plus 2, okay? So as we stretch it out to here, right, that's going to be our A. And the numbers from the last problem were A is 0.1, so our K was 19.6, and our A is 0.1. So it's a plug and chug. And you get energy of 9.80 times 10 to the negative 2 joules. So pretty small number there when we talk about that. Now B, we want A to be half, so it's just 0.1 divided by 2, or 0.05. So it's going to be E is equal to 1/2, 19.6, 0.05 squared. And our energy is 2.45 times 10 to the negative 2. Joules. So this, okay, is based on position, right? So that's going to be our potential energy at half. To find our kinetic energy, we just take this number minus that number, and you get 7.35 times 10 to the negative 2 joules of kinetic energy. And again, here, there's no speed, so it's all potential, right? But as it gets closer, it speeds up as potential decreases. So potential goes down while kinetic increases. And when we get to this point, back to the equilibrium, the kinetic will be all we have, and we have no potential.
Spider web. A spider of mass 0.30 grams waits in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of about 15 hertz. We want to know the value of the spring stiffness constant for the web, and at what frequency would you expect the web to vibrate if an insect of mass 0.1 grams were trapped in addition to the spider. So we're adding some more mass to the picture. Do it now.
All right, so we're talking about the spider web problem. It says estimate. I'm going to use numbers because I like to have numbers in front of me. But frequency, 1 over 2 pi square root of k over m. Before we could do any work, obviously we got to find the stiffness constant k. So we got to work and try to find k. And that could pose some problems here. The first thing I would do is bring 2 pi over. So I get 2 pi f equal to the square root of k over m, and then square everything, which gives me 2 pi squared f squared equals k over m, and then just multiply both sides by m. So k is equal to that. And now we just got to substitute numbers in. So we know the mass is 3.3 grams. Oh, that's the spider. Yeah, 0.3 grams. Okay, so we have 0.3 grams. Got to convert it to kilograms. So 0.3, 1, 2, 3, 0.0003 kilograms times 2 pi squared. And the frequency in the problem is 15 hertz. So 15 hertz squared. So I put all those in my calculator, and I get 2.7 newtons per meter. So that's my spring constant. Now I can look at letter B, and letter B says, at what frequency would you expect the web to vibrate if the insect of mass 0.1 gram were trapped inside in addition to the spider? So now we have to add some mass, but we're still solving this the same way. So I'm solving for f, 1 over 2 pi, square root, my k is going to be what I solved for, 2.7. Now the mass, instead of being 0.003, I have to add to that the mass of the bug, which is, we said was 0.1 grams. So it's going to be 0.123 zeros and a 1, and we add those two together. So add together, divide these two, add together, square root, multiply by 1 over 2 pi, and we get a frequency, in this case, of 13 hertz. So our frequency is going to drop by adding more mass. We add more mass, our frequency will go down. Should make sense mathematically, and it does.
Vibrating floor. A large motor in a factory causes the floor to vibrate up and down at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. We want to estimate the acceleration of the floor near the motor. Do it now.
All right, so the vibrating floor, a large motor in a factory causes the floor to vibrate up and down at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. We want to estimate the max acceleration of the floor near the motor. All right, so we want to find acceleration. Acceleration max will be force max over m, all right? That's Newton's second law. Remember, force is kx, so A max is equal to kx over m. Now, I can do some work here, and this is where we can take equations and put them together. I'm going to just do a quick little factor job here and say x times k over m, right? And I'm going to substitute something in for k over m using my frequency equation. So multiply both sides by 2 pi. 2 pi f is square root of k over m. Square everything. 2 pi squared f squared equals k over m. So now I can take this and substitute it in there. So A max is equal to x times 2 pi squared times my frequency squared. And now I just substitute, my x was 3 millimeters, right? So I'm going to put that into meters. So 1, 2, 3, .003 is my x, 2 pi squared, times my frequency, which we said was 10 hertz. So I go 10 squared. And I math it out, and I should get an acceleration of 12 meters per second squared, which is greater than the acceleration due to gravity. And that's why we see that vibration happen, when we have that acceleration being greater than the acceleration due to gravity. So that's the answer we would expect, at least something bigger than 9.8.
And then we're going to start with this equation, right, to find displacement. So the displacement of an object is described by the following equation, where x is in the meters and t is in seconds. So here's the function, right? Amplitude, cosine, angular velocity is 8, and then t is time. So we want to find amplitude, frequency, period, max speed, and max acceleration for this function. Do it now.
All right, so here's our equation. Just as a point of reference, I'm going to look up here to find things, right? Here's what we know. We know that if we want to find our amplitude always be before cosine in the formula, so that we know our amplitude is 0.30 meters. So that's the answer to A. B is asking the frequency. So now B want to know the frequency. So 2 pi frequency t, there's our t, so this is going to be 8. So 2 pi times frequency equals 8 divided by 2 pi. 8 divided by 2 pi will be our frequency. And 8 divided by 2 pi is 1.27. So our frequency is 1.27 hertz. C. C is asking us to find the period. Period is just 1 over frequency, so period is 1 over 1.27. So period is going to be, in this case, 0.79. So not even a full second, 0.79 seconds. D wants to know the max speed. Vmax, and this was derived from another equation, but I'll give this to you. It's 2 pi AF, Vmax, 2 pi A times frequency, right? Amplitude times frequency. So 2 pi, my amplitude is 0.3, and my frequency is 1.27. And I solve away with that, and I get 2.4, so my max velocity is 2.4 meters per second. And then letter E is asking for the max acceleration, all right? So remember, A max, we've done this a couple times, but you can see this equation. It's important to understand this. It's force over mass. Remember, force is kx, so it's kx over m. So A max is kx over m. And then we can look at kx, and we know km is equal to, and this was something that was given earlier, 2 pi frequency squared. So I can put that in for km. X, in this case, is our amplitude. So A max is 2 pi f squared times amplitude, which we know is 0.3. Our frequency is 1.27. And then I just mash all those buttons on my calculator, and I get an answer of 19 meters per second squared.